Hello, everyone, and a very warm welcome to Kognito Key. I am absolutely thrilled to have you here today. You know, if you've ever stared at a massive electrical grid and wondered what on earth happens when things go wrong, like really, really wrong, well, this explainer is exactly for you. The thing is, power grids are incredibly complex beasts, and when an electrical fault happens, it's almost never neat. Usually, it's just this chaotic, unpredictable, asymmetrical mess. But engineers have this absolutely brilliant mathematical trick up their sleeves to tame all that chaos. Today, we're going to demystify power grid faults by mastering a foundational concept. It's basically our ultimate problem-solving hack, and it's called sequence impedance. So let's dive right in.
So first things first, what exactly is sequence impedance? At its very core, it's just a way to describe how a power system network behaves under those really tricky asymmetrical fault conditions. Because think about it, every single component out there, whether we're talking about a static transformer or some massive rotating synchronous machine, they all react totally differently the second the system loses its balance. Sequence impedance is amazing because it allows us to map out that unpredictable behavior. We do this by measuring the resistance, or impedance, that's offered to different phase sequence currents. It literally takes a completely tangled, messy physical reality and translates it into manageable, measurable metrics.
Now, to make all this crazy grid behavior actually manageable, we engineers use a classic divide and conquer approach. We essentially break the total impedance down into three distinct types: positive sequence impedance, negative sequence impedance, and zero sequence impedance. You can kind of think of these as three separate mathematical pathways, or lanes on a highway. By separating a messy, overlapping fault current into these three neat little categories, evaluating the network suddenly shifts. It goes from being this impossible guessing game to a really precise, solvable equation. It's pretty cool, right?
Okay, so the absolutely crucial starting point here is the positive sequence. This represents the impedance offered by the network to the flow of positive sequence current. Picture a perfect, healthy system. In that ideal world, all the electrical quantities are numerically equal, they're perfectly balanced, and they are displaced from each other by exactly 120 degrees. This is the normal, forward-moving energy of the grid. Honestly, you can just think of it as the power grid's ultimate Zen state. It's that harmonious baseline where everything is behaving exactly as it should be.
But when an asymmetrical fault hits, that perfect 120-degree harmony is completely shattered. And that is exactly when the remaining two sequences immediately kick in to account for all that new chaos. First up, we've got the negative sequence. This is the impedance the network offers specifically to negative sequence currents, which is essentially the backward rotating energy that gets caused by the fault. And then second, we have the zero sequence. This one handles the zero sequence current, and we often associate this one with those really dangerous ground faults. Together, they directly correspond to the chaotic energies unleashed during a failure, giving us a super clear way to measure the exact imbalance.
Now, you might be sitting there wondering, okay, but how do we actually calculate these specific values? Well, it all boils down to a beautifully simple ratio. Think of it kind of like Ohm's law, but specifically tailored for electrical faults. The impedance of any sequence component is found by just taking the phase sequence voltage and dividing it by the phase sequence current. That's it. This unified, super straightforward formula applies across the board. So whether you're calculating for the positive, the negative, or the zero sequence, it just elegantly cuts right through all that complexity.
And guys, this brings us to what is arguably the single most important principle in power system fault analysis. The rule is, there is no mutual impedance between various symmetrical components. Why is this the holy grail for engineers? Well, because it means the positive, negative, and zero sequences do not interfere with each other at all. Since there's no mutual impedance tangling them all up, we are totally saved from having to solve one massive, impossible matrix of equations. Instead, we get three completely independent, easily solvable formulas. I mean, it is literally an absolutely brilliant mathematical hack.
So, as we wrap up today's explainer, I really want to leave you with this final thought. How will you use sequence impedance to simplify your very next fault calculation? Just remember, by breaking down the messy realities of grid failures into these independent, manageable sequences, you have the exact mathematical tools you need to bring order right back to the chaos. Thank you so much for joining me today on Kognito Key. If you found this explainer helpful, please make sure to hit that subscribe button, give this video a like, and share it with your fellow engineers. I'll see you next time.